Now that we are acquainted with the 3D version of the Hooke's law that incorporates the axial stresses, the shear stresses, the axial strains and the shear strains, and as well as the Poisson's ratio, and we derived all these different relationships between the strains and the stresses, and we can do the transformation, right? Next, what we are going to look at are two special cases of these different instances of the stresses and the strains. These are known as the plane stress problems and the plane strain problems, and you will see that many of the engineering problems that we work with on a day-to-day basis can often be categorized into plane stress problems or the plane strain problems. And in this lecture we will learn that what kind of scenarios or in what kind of cases a problem can be classified into a plane stress or a plane strain problem. Now, before we go ahead and do that, I just want to jog your memory into the 3D version of the Hooke's law that we looked at, right? So this is what we covered in the previous lecture, that when we have both the axial case as well as the shear case, right, in that particular instances I can write my axial strain as these are the three primary axial strains that I have, and these are the three primary shear strains. Now remember, the axial strains, for example, sigma x is not only dependent upon your epsilon x is not only dependent upon sigma x, but it also depends upon the stresses along the y direction as well as the z direction, and they're related using the Poisson's ratio, right? Now remember that whatever you're looking at, these three different strains and these three different stresses is are the strains for the most generalized case where a particular body that you have or a small element within the body have these strains and have these stresses, both the axial as well as the shear, acting along the different directions, right? Now, special cases, as you can imagine, two of the special cases, the plane stress and the plane strain, as I said, are essentially derivatives of the general state of stress. The general state of stress, you have the stresses and the strains acting in all the different directions, right? And two special cases of these ones where you will see the stresses disappear about a particular direction or the strains disappear about a particular direction, depending upon the type of structure, depending upon the boundary conditions, depending on the type of loading. So this is what we are going to look at, right? So let me maybe just highlight it and write it here. The two focuses we are going to have now are the plane stress and the plane strain, right? So let's look at that under which categories or which set of problems are plane stress problems and which set of problems are the plane strain problems. So let's start with the first one, the plane stress problems, right? So the plane stress problems is applicable to members which are thin, right? When members are thin and you're essentially applying the load along only one particular plane such that the stresses about the other plane vanishes, right? So for example, the one that you see over here is that this is an example of a spanner or a wrench, right? Where remember that how do these operate? So you typically have a bolt over here, right? And you take the bolt and you essentially rotate your spanner to tighten that particular bolt that you have over there, right? I don't have a spanner in my office, but maybe I can try to do a small demonstration using a similar kind of a mechanism. So for example, if this is my this is a bottle, of course, but if you are looking at this particular plane, right, the end of the bottle, suppose this is the xy plane over here, and say the end of my umbrella over here is the spanner that I am looking at, right? So it is essentially, this is how a spanner works. You essentially tighten the bolt or you loosen the bolt like that, right? So if you take a look at this one, my forces which are applying, if this is my xy plane over here, when I am rotating or when I am pushing or when I am pulling over here, all these forces are in the xy plane. There is no force which is acting along the z plane that is perpendicular to the xy plane over here, right? So I hope this idea is clear that how the the plane strain problem works, right? And if you see the example of the spanner which I just showed you over here, it works essentially in a very similar fashion. You have the spanner and you sort of do this kind of a motion. Another very practical example is that the one for the plates. For example, if I have a thin plate, if you imagine this as a plate over here, and it's a thin plate y, compared to my x and y direction, my z direction is extremely small, right? So this is a thin plate. So thin plates are typically loaded in plane. So you have the in plane loading. For example, you pull it like this. Thin plates never get this out of plane loading, because of which the plate might easily buckle. So the application of thin plates are mostly, you have these in plate kind of loadings which are there, right? So this is also an example where if you see this, if this is my xy plane over here, all the loads that I am applying are along the xy plane. I do not have any load in this particular z direction that is there, right? So as you can see within this figure as well, right, if suppose the face of this plate is the xy plane, all these forces that you are seeing act along the xy plane. There is no force along the z direction that you have. So what does this essentially mean? So this means that if there are no forces along the z direction, that automatically means that some of the stresses vanish. So because the forces are related to the stresses, or in other words, the stresses are actually related to the forces, right? So if you don't have forces about a particular direction, the stresses automatically vanish, right? For example, the bottle example and the range example which I was showing you, in that particular one, you're not applying any shear about the z direction, you're not applying any normal force about that particular z direction. So essentially your sigma z, right, your tau xz and tau yz, any force that has to do with the z direction, it essentially vanishes. So if for the generalized state of stress, remember that small element that we were looking at which had the stresses along all the directions, now if you impose this condition, this somehow becomes like this. I have my sigma x, I have my sigma y, I have my tau xy, but along the z direction, this is my z direction, along the z direction I do not have a sigma z, I do not have a tau xz, I do not have a tau yz as well. So the generalized formulation that we looked at, how does that change now? Let's go and take a look at that. In the generalized formulation that is there, right, this was the generalized form of what we had. So now that if we do not have the sigma z and the tau xy and the tau xz, so as you can tell automatically that this particular element is going to vanish, because your tau xz equals to 0, your tau yz equals to 0. So this is also going to vanish, right? And in these three equations over here, which component is going to vanish? Well, none of the strains are going to vanish, because the strains depend upon the stresses in the other direction. So only within these equations, that particular component which only depends upon the sigma z, that is going to vanish, because my sigma z, remember, it is equals to 0. So here this component is going to vanish, right? In the second one also sigma z equals to 0. So this is going to vanish. And in the third one over here, sigma z equals to 0. So that is going to vanish as well, right? No, epsilon z is not equals to 0. Sorry, I meant to write that this particular component over here, that your sigma z is essentially 0, right? So you say now the strains become kind of simplified, and if you come back and if you substitute over here, if you do the transformations, what you will find, as it has to corroborate with what you saw in the the generalized state of stress after you remove the sigma z, tau yz and the tau xz, that this is going to disappear, this is going to disappear, and if you come back and if you put the values over here, you will see that this particular component is going to disappear as well, right? If you come back here and you put the value of the epsilon z and the epsilon x and epsilon y, you can try doing that exercise and you will see that this one also disappears, right? So now that we have this one, the general set of equations, after we impose these conditions, you have a reduced set of equation, as you can there, right? So this is the reduced set of equation. That's what it looks like. Remember that for the expression of the epsilon x that we have over here, now you do not have the nu sigma z divided by E, which we cancel in the last page, right? You have a reduced equation for your epsilon y, and it's amazing if you see that your epsilon z, although you do not have a stress about the z direction, you do not have a sigma z, it still depends. And why? It depends, you have guessed it right, it depends because of the Poisson's ratio. It depends upon the Poisson's ratio. So it still depends upon the stresses along the x and the y, but through the Poisson's ratio, right? And among the shear strains, we have our tau xz and the tau yz vanish. So we only have your gamma xy, which is dependent upon the tau xy, right? And this is again the the transformation that you have been doing from the strains to the stresses. So this is just the transformation. You can put in the equations for the stresses that we looked at in the last page as well, and you will essentially get the same set of equations that is there. Okay, so that is the case of the plane stress problem. So from the name itself, since the word stress is involved, we are looking at the cases where about a particular direction your stresses vanish, right? Now from the name, now can you guess what is going to be a plane strain problem? Yes, you're right. Plane strain problems are those, from the word strain itself, you can tell that about a particular direction, the strains are zero. So previously we looked at about a direction, the stresses were zero. Now we are going to look at the plane strain problems where about one particular direction, the strains are zero. So let's look at some plane strain problems, right? So plane strain problems, as you can see from the figures over here, they have a wide range of engineering applications. For example, one of the very well-known applications of the plane strain problems are the dams, right? So if you take a look at this particular dam over here, dams are water retaining structures. See, this is the body of water which the dam is holding back, and this is your normal functioning roads or something that you have, and this is that entire dam that you're looking at, right? So in this particular dam that you have over here, right, if you think about the deformations of what is going to happen in this particular dam, see, it has at the left end over here and at the right end over here, it has these restrictions, right? So at the left end, it is kind of restricted. At the right end, it is also restricted over here. So it has essentially no movement, no deformation, no allowed deformations in those two directions, because the dam has to be in place, right? So there are no movement about that particular direction, right? The dam can have movement about the other directions, but essentially what you are doing, that you are restricting this movement as well as you are restricting this particular movement over here. The dam can still move about this particular direction and a vertically upward direction as well, right? It can have some amount of elongation, maybe due to temperature, due to the stresses of the water. You can have some amount of deformations about this direction, but no deformations allowed about these two particular directions over here. Essentially similar to this one, as you can say, this is just the hypothetical representation of the dam that you have, right? Here you have all the forces and the deformations in this one, but no deformations is allowed about this particular axis over here. Another example is gas-filled cylinders. When you have gas-filled cylinders along which the both ends of the cylinders are sort of fixed, you're not allowed to move. So suppose this is my z direction, you're not allowing any kind of deformations, whether, and remember, strains are related to deformations. So if you're not allowing any deformations about the z direction, that means you're not allowing any strains also along the z direction, right? What are the kind of strains that you're not allowing? You are not allowing the normal strains, you're not allowing the shear strains. So any kind of strains you are you are restricting about that particular direction that is there, right? So if we just go ahead and take a look again from the generic formula, if we just reduce it over here, now what we are looking at, that about say a z direction, if you take a look at our element over here, about this z direction, you're not allowing any amount of strain. So essentially your epsilon z becomes equals to 0, your gamma xz becomes to 0, and your gamma yz becomes equals to 0 as well. See, analogically, in addition to these two examples, another example which I can give you, remember when we were looking at the thermal stresses, right? When we were looking about the thermal stresses, you had this, bar. Now if you see this one, right, if this is my xy plane over here, so this is my, say, x, and this is my y, and say this is my z direction that is there. Sorry, I probably misspoke, right? So if this is my z direction, my x direction is going to be about, say this is my x, right? This is my z and this is my y, right? So when you are heating this bar, and if you have it clamped over here, if you're heating this one, right, then in that particular case you are going to have maybe expansion about this particular, you can have expansion about the y axis, you can have expansion about the x axis over here, but about the z axis, imagine if this is the z axis, since it is clamped, you're not allowing any movement, right? So all the strains, the epsilon z which you are having along these two z axes over here, they are restricted. Your tau xz is your gamma xz is restricted, and gamma yz is also restricted, right? So now that you have over here, now as you can tell that we can go back to our generalized set of equations, and we can cancel some of the strains, and we can see what is a consequent effect on the stresses that you are going to have, right? So again, coming back to the generalized form, now that we know that my entire this epsilon z, since I'm not allowing any epsilon, this entire thing is going to vanish, right? This thing is going to vanish as well, and this thing is going to vanish as well, right? So these three equations go for a toss, right? We are still going to have this one and this one. So my strain vanishes, so do my stresses also vanish? Maybe not, because my stresses are also dependent upon the other kinds of strains which are there, right? So if we just go back and if you take a look at the reduced set of equations, remember, as we just marked in the previous page, our epsilon z vanishes, our gamma xz vanishes, and gamma yz also vanishes. The other strain quantities are there, and as we did, this is simply a transformation. You can apply, or you can input your epsilon z and gamma xz and the gamma yz in the previous equation. You will essentially get the same set of the transformed equations. Right? So these are the two categories of problems which are there, which are the plane stress and the plane strain problems. And what we just looked at are several of the engineering examples where you will see that several of the practical life scenarios or the practical life problems can be sometimes reduced into the plane stress and the plane strain problems. You will learn more about these things in some of the advanced classes that you would take when you talk about plate theory or shell theory and so on. You will see that some of those problems can be reduced to these plane stress or the plane strain problems that we have over here.